There's a bunch of chicken crossing the road. I'm not sure if the video is clear for you guys, but a bunch of chicken crossing the road. This is driving on self-driving software, and it's just waiting for the last chicken to cross here. It's patiently waiting. The chicken crosses the road, and then the car proceeds on its own. This is all just driving on its own.
Well, I think it's going to say, look, it's going around him. It's going around him. Oh, look, it's changing its mind. It's backing up to go around them. Look at that. It backed up to go around the geese.
This is crazy. This is crazy.
Some examples of like what that kind of like corner case data might look like. And then this is very, very useful data to train on. And this is not normally accessible. You can't stage this that easily because it requires the stationary scene, the speed of all the vehicles. And Tesla has a unique advantage here that it can tap into the entire fleet to get this data. We find that the approach that we took is quite scalable. It scales across different vehicle platforms, different spatial locations, different weather conditions, and overall offers a very safe, comfortable, and fast ride to the users. It's not just scaling self-driving to all the vehicles, but also scaling it to other forms of robots, the humanoid robots too. And the same technology that we developed here for self-driving transfers most seamlessly to other forms of robots too. Tesla is all in on robotics. The entire company is just focused on producing intelligent, useful, large-scale robots for helping everyone in the world.
Tesla's AI lead and Gigabrain, Ashok recently gave an epic presentation, some behind the scenes of Tesla's approach to autonomy and some of their broader AI efforts, much of which is applicable to the humanoid robot and who knows what else. If you own Tesla stock, or if you don't own Tesla stock, you would be a moron not to watch this entire presentation in full. In fact, we're going to watch this in full and I'm not going to interrupt. I'll share my thoughts at the end. And I implore you, watch the whole thing. Pay attention. A multi-trillion-dollar disruption is underway and Tesla is leading the charge. Now, this presentation does get a little technical, but please don't skip, don't tune out. Stick with it. Trust me, you're going to want to hear everything he has to say. Then I'll share my thoughts at the end.
My name is Ashok. I lead the Tesla AI team here at Tesla. So excited to be here. I couldn't be in person. It's a bunch of other company work here, but nonetheless, excited to share our recent progress. This is the work of the Tesla AI team over the last several months. So I'm talking on their behalf here. I'd like to start with some of the recent accomplishments that the team has achieved. Earlier this year, around June, July, we launched our Robotaxi service, where if someone was in Austin or in the SF Bay Area, they can hail a Robotaxi service from Tesla. And then in Austin, below 40 miles per hour, you can get a car without anyone inside the passenger seat. So it is just driving using these cameras and neural networks and adapting to real world conditions. We also did this thing where we delivered the first customer purchasable vehicle from the Tesla factory in Austin directly to a customer's home somewhere else in Austin. And we covered over 20-30 minutes of driving across highways, city roads, parking lots, etc. to deliver the car. You can see the car driving itself. And this is a production vehicle out of the factory using production cameras, the same computer that's in every car and so on. Every Tesla that's manufactured in the US also delivers itself from the manufacturing line all the way to the loading docks. That's like a couple miles away. So this year we made a lot of strides in autonomy, and we continue to scale the technology to be even more robust and resilient, so that we can go to even more locations, have no one inside the car, and so on. Today, I'd like to touch on some of the technologies that help power this self-driving. So first of all, we switched to having a single large end-to-end neural network that can take in pixels and other sensor data as an input, and then just produce the next action as an output. So this is what's driving the car. It no longer is doing explicit perception of like vehicles, road boundaries, or things like those. They can be implicit and they can be trained as auxiliary things, but then the entire thing, the raw video streams go in, and then the actual actions to take are produced by the neural network. And it's been so for the last few years, and this has been extremely good. The reason being, we used to work on an explicit modular approach because it was so much easier to debug and so on. But what we found out was that codifying like human values is really difficult. For example, you could, in order to brake for an obstacle or go around, you could go as fast as possible and then brake a bit later, or brake earlier for more smooth driving. And this really comes down to an alignment of preference to human values, as opposed to there's one objective value of like how much braking and when to apply. You don't want to brake too early either, because then it'll be too slow. And if you don't want to brake too late either, then it's too uncomfortable. And this varies from situation to situation. The amount at like low speeds versus high speeds is very different. So it's really hard to codify what humans actually want, and you can't write it in code, at least not very well. And also the interface between traditional perception and planning is very ill-defined. It can be very lossy and lose critical information, where you might need to propagate the uncertainties through the entire system. That's really hard. Going to end-to-end neural network also allows for your compute to be homogeneous, because if you have traditional branching compute, you can have non-deterministic amounts of latencies, and in a real-time system, you don't want to have the kind of latencies. You want to have predictable deterministic latencies, and such single neural network doing the entire thing offers that. And overall, this is what we believe as the the right path to solving robotics, as opposed to this kind of modular brittle systems that were developed earlier. Here I have to give a few examples of like why this is hard. For example, this vehicle is driving on like a bidirectional road, and then to avoid this puddle, you got to go to the oncoming side. If you have to write this using explicit cost functions, it's going to be really hard, because typically you don't want to go into the oncoming side. But then what is the pain of driving through a puddle versus the risk of going through an oncoming lane is like hard to write in explicit code. But here, obviously, if you look at the scene, it's pretty obvious that you can go here. You have a lot of visibility. There's no oncoming vehicle coming, and you should definitely go into the oncoming side. It's also like hard to understand intent. For example, here on the left side, there's a bunch of chicken crossing the road. I'm not sure if the video is clear for you guys, but there's a bunch of chicken crossing the road. This is driving on self-driving software, and it's just waiting for the last chicken to cross here. It's patiently waiting. The chicken crosses the road, and then the car proceeds on its own. This is all just driving on its own. In this case, the car was smart enough to understand that the chicken actually out crossing the road, and was patient enough, even though there was no collision risk. It was just the right thing to do. But in other cases,
What's it? Well, I think it's gonna say, look, it's going around him. It's going around him. Oh, look, it's changing its mind. It's backing up to go around them. Look at that. It backed up to go around the geese.
This is crazy. This is crazy.
yeah. In this case, the model understands that the geese are actually not crossing; they're just like stationary, and decided to reverse and then go around them. So it's not. This is something that it's very hard to write in explicit code. What is the right thing to do here? But looking at the scene end to end, and for humans too, it's pretty obvious what was the right thing, and that is why end to end is way better than a modular approach. That said, it's not that easy to develop such a system. It's pretty difficult, in fact. And I'd like to touch on three different aspects of it that make it really difficult. First is the curse of dimensionality. What I mean by that is that the input context length is quite enormous. Especially our cars have 7 or 8 cameras depending on the vehicle. Each produces 5 megapixel camera streams running at high frame rate. And even if you want to have 30-second context or something like that, along with the other necessary inputs the routes and then the vehicle speed and other kinematic data, it can easily be more than billions of tokens, 2 billion tokens for a 30-second context window. And if you naively just use some kind of WIT giant transformer, it's just going to be really difficult task of mapping 2 billion tokens down to roughly 2 tokens, which is what is the next steering and acceleration that the car should take. Thankfully, Tesla has a huge advantage here. which is the Tesla fleet is quite large. So it's basically has access to the Niagara Falls of data. And it's up to Tesla to use this data to solve this problem. You don't want obviously spurious correlations from the 2 billion tokens down to the 2 tokens. You want the right correlations as to why those 2 output tokens must be the right tokens. So what we do is we refine this 500 years of driving, which obviously is more data than we could ever store on our clusters, to the essential amount of data, which covers the overall spectrum of driving. There's different ways we can collect this data based on like explicit triggers or small neural networks targeting specific scenarios, or like constantly evaluating what the model predicted versus what actually happened, and things like those. We can use such tricks to extract just the right amount of data, and the right quality and the kind of data that we need for our training. Here's some examples of like what that kind of like corner case data might look like. These are examples in manual driving, like people are just still driving, and then once every now and then they encounter such rare scenarios, and we can have triggers that catch these, and then this is very, very useful data to train on, and this is not normally accessible. You can't stage this that easily because it requires the stationary scene, the speed of all the vehicles in state space. This is really hard to achieve. And Tesla has a unique advantage here that it can tap into the entire fleet to get this data. Once we get this data, you can use this to train our end-to-end model, like I mentioned before. And it just generalizes to extreme scenarios like these ones, and not just reacting at the last second, but proactively safe. I'd like to show a demonstration of like how that manifests. Like this is again a self-driving system in operation here, just on a highway. I'd like to watch the video for a second. Yeah, here the car in front of us spun out and then hit the barrier, and the self-driving system pulled over safely. But what is quite interesting is that if you watch the video again, I like pause where the car, the ego car brakes. Like here, if you notice this car here, it's like spinning out of control and it's going to hit the barrier and it's going to bounce back into our lane. It requires so much intelligence to know that this is not a first order collision here, because at this frame, the Tesla already determined that this vehicle, there's something wrong here, and started applying the brakes. It did not wait for the car to hit the barrier and then bounce back for its velocity to change or something like that. This is a second order effect that it needs to model. And it could have also attributed this to a lane change of this vehicle, but it did not. It understood because it was requesting roughly 4 meters per second square of braking, which is not a light amount of braking. And this is only possible if you have a ton of data and cover all these corner cases. And that is how you can provide both safe and also a smooth ride, because a less intelligent system would wait until the direction has changed or actually some bad event has happened. But it requires a lot of intelligence to understand that something is going wrong way before it actually goes wrong. And that is what you get with an end-to-end system with a ton of data. Secondly, so it's an end-to-end system. How do you guys debug? How do you actually develop this thing? If something goes wrong, how would you know? Just because it's an end-to-end system does not mean that it cannot predict anything else. The same model can be prompted to predict arbitrary things, including 3D occupancy, other objects, traffic lights, traffic signs, the road boundaries. Even just in plain language, you can ask it why it made some decisions, does it understand the scene, and so on. All of this helps interpret the model's understanding and also sort of like give some guarantees around the safety of the entire system. So in practice, it sort of looks like this, where you can take in arbitrary sensor data and prompt it to produce arbitrary things. But in the end, the only thing that actually matters in the car is the control actions that it produces. Everything else is auxiliary, but they can be quite helpful for predicting the correct control actions. One specific task that I would like to go over is the Gaussian splatting, which in the last few years has been quite prominent in the field. But what I'm showing here on the left side is the traditional Gaussian splatting, I know it looks really bad, and it's not like taking some bad example and showing. The problem typically is that vehicles drive in sort of a linear fashion going forward, and there's not a ton of baseline. And because of this, if you just took the same camera views of the vehicle's motion and ran traditional Gaussian splatting, I don't know, Nerve Studio or what have you, with the same camera views, the views close to the train views look great. But then if you go to novel views that are far away from the train views, it breaks down quite a bit. But what we have in the middle column here is Tesla's variant of Gaussian splatting, where the same model can produce Gaussians. It generalizes much better with the same limited camera views that the left side has. It can also produce semantics as shown in the third column. And the cool thing is that it can run ridiculously fast compared to traditional Gaussian splatting, which can take tens of minutes. Also requires steps like call map or something else to produce the camera poses. It requires initializations from these kind of explicit solvers to do a good job. So you can see that this can update to scenes quite rapidly. If you use the same traditional splatting, a lot of novel views might look blurry or like fuzzed out. But as I'm rotating here in 3D space, a lot of the structure remains intact. And such interpretable representations can be used to debug the system. Like if it's going faster or slower, you can easily observe, okay, is it safely avoiding some obstacle or not? Like I mentioned earlier, we can also use natural language to interact with the model. The same model can sort of like point to things, explain why it made some decision. We shouldn't need all of this to drive the car in real time, but then if you do need it, you can always think longer and produce reasoning tokens to then produce the right action that is consistent with the reasoning of the entire thing. And again, it can be the same model that's running in the car, but based on the situation can use it or can directly produce the control actions if it's not required to reason in such detail. Because if you keep reasoning in detail for every single thing, then it's going to take too much latency. But then wherever it's needed, it could reason longer to produce the right answer. The last piece that I'd like to touch on is the evaluation, which actually is the most difficult of these three problems I mentioned. If you just train a bunch of data from drivers and then train models and just like scale it, your open loop performance like look amazing, but then it may not translate well to how the car actually drives. There's a lot of reasons for this. I don't want to get into the details there, but then it is a very important problem that requires a lot of attention to get good performance out of the system. It also requires like thorough evaluation sets. It's not just, if you randomly sample data from your fleet, most of it is going to be boring highway driving. You don't want to just be evaluating there. That's where the early data engine approach that I mentioned comes in handy, where we can build a balanced, fully covering eval set, which is extremely important but very tedious work. One great thing we figured out was that we can use the cheap to collect state action pairs, invert it, and then basically build a world simulator where given past state and then actions, it can synthesize newer states, this condition on the actions. This is quite easy to collect because you can get it for free. You don't need optimal driving or something like that. Any kind of trash driving is good enough for this kind of simulator because it needs to simulate the edge cases. Then once you have that, you can connect that with our policy neural network that's driving the car, and then they can both run in sequence in a loop to sort of simulate the world. So here's an example of our rollout through a learned neural network simulator. I'll let you watch the video for a second here, but the entire thing is generated video. There's 8 cameras. The top row is all the front cameras of the car driving forward. The middle ones are the left and the right side cameras, and the bottom row is the rear-facing cameras. all 8 cameras are generated simultaneously by a single neural network, and takes action as an input, so you can steer the network. I'll show you in the next couple of slides how that can work. But yeah, I'm usually blown away by the consistency of generation across different cameras. Even the vehicle rims are consistent, the traffic lights, and this is over like a minute and a half long generation of 5 megapixel video streams. In addition, you can take like past issues, like take a year-old issue, and then you can rerun the latest neural networks to see how they would perform. On the left side here was the original failure where it was maybe a bit too close to the pedestrian. And then on the right side, we are evaluating a newer neural network that's driving the car. And you can see that the policy starts offsetting way earlier as soon as the pedestrian emerges from behind the car. And it's super useful for such kind of evaluation, because you don't want to just reevaluate on newer mileage. You just want to, if you have a database of older issues, you just want to replay them and verify that you are doing a good job on these past issues. You can also synthetically create new issues. In this case, the original video on the left side, that vehicle was just going forward on its own lane. But then on the right side, we can make condition the vehicle to cut across our path and then inject this kind of adversarial event to test the system's corner cases. And you can see that the rest of the scene remains consistent. All the other vehicles are moving the same way, just that this one vehicle cuts across. And that's how you can make lots of synthetic data sets to verify the corner case performance of a self-driving system. If you are fine with reducing the test time compute a little bit, you can get close to real-time rendering performance. This is the same model that's rendering the 8 cameras with lowered test time compute. And you can see that you can actually drive this in real time. The FPS is high enough, even though it's generating 8 5 megapixel streams in parallel. So obviously you can see that it's responding to the user's driving commands. They can like steer and brake and then sort of like navigate the world just as if they're driving in the real world. But the entire thing is neural network generated video streams. I think the driver is trying to do something adversarial by going on the curb and then just demonstrating that the generalization of the simulator is quite good. Yeah, this entire video is 6 minutes long, and you can just have consistent video generation for a very long time and responding to control commands. You can hence imagine like how this tool can be quite powerful, both for evaluation purposes, but also for closed loop reinforcement learning, where you can just let the car drive and then verify that it doesn't collide with anything for a very long time. So yeah, what's next? We want to scale the service to be much better, and then unlock the entire fleet of Tesla vehicles to be fully autonomous. This is the Cybercab, which is our next gen vehicle, which only has like 2 seats and designed for the purpose of Robotaxi. It's going to have the lowest cost of transportation across even public transportation, and it's all powered by the same neural networks that you saw earlier. We find that the approach that we took is quite scalable. It scales across different vehicle platforms, different spatial locations, different weather conditions, and overall offers a very safe, comfortable, and fast ride to the users. There's one more thing, which is it's not just scaling self-driving to all the vehicles, but also scaling it to other forms of robots, the humanoid robots too. Tesla builds humanoid robots. We call them Optimus. And the same technology that we developed here for self-driving transfers most seamlessly to other forms of robots too. I'd like to show one example here. Like the video generation also works for Optimus. So this is Optimus navigating around the Tesla factory, and all of these are generated videos. And you can see that they are all quite consistent. You can also, just like how we did for the car, action condition it. So here, the top left is the robot just going straight. That was the ground truth. But then you can have different actions like going left or right or some other direction, and then it can correctly generate the pixels for the action. And it's the same neural network with just some more data added from Optimus generalizes to other robot form factors too. So yeah, in conclusion, Tesla is all in on robotics. The entire company is just focused on producing intelligent, useful, large-scale robots for helping everyone in the world. And if you are working on AI, robotics, computer vision, etc., I'd highly encourage working at Tesla because it has like extreme real-world impact. It's fully in on solving robotics. The team is super pumped. I think it's a great place, and this is the best place to work on AI right now. Thank you.
Boy, oh boy, do I have a lot of thoughts now. First and foremost, if you didn't notice, the technical details might have given it away, but this was not a presentation for Tesla investors, although they'd be brain dead not to watch it. Congrats for making it to the end. This was clearly and solely intended as a AI recruiting effort to hire some of the biggest brains on the planet to work at Tesla on these epic AI projects, Autonomy and Optimus humanoid robot. Obvious things are obvious. That's the point. The fact that investors get the opportunity to listen in on this, to see the update, to see Tesla's recruiting efforts for the AI gigabrains out there is just enormous. What other companies out here are doing these types of presentations? Oh, wait, no one's even working on these projects. Bro, what a silly question. Come on, bro. No one's even trying. But this is important. Now, I just want to recap and share some of the thoughts throughout this presentation. First, we heard some of the milestones. Since late June, early July, Tesla launched their Robotaxi service in Austin, and since then, by the way, there's been multiple expansions, including the dick-shaped geofence just because, massive flex if you know, you know. Launching in California, Tesla's first vehicle in Austin rolled off a production line at the Gigafactory and drove about half an hour to deliver itself to a customer autonomously. We also heard that every US-made Tesla vehicle now is driving itself from the manufacturing lines to the loading docks a few miles away. No other company on the earth, anywhere, is doing this. We then heard some details about Tesla's complete end-to-end approach, which, as we know, is the way to solve autonomy. They deleted hundreds of thousands of lines of code. We heard lots of detail about why this makes sense, but surely if you're a Tesla investor, you've been paying attention, you know this. It's extremely challenging to write a line of code for every possible scenario and situation. Much better to train end-to-end on video of good human drivers and let the FSD software learn what to do in a specific situation without hundreds of thousands of lines of specific detailed instructions for every possible variation under the sun. Examples, by the way, why did the chicken cross the road to get itself featured in a presentation on Tesla AI? Yeah, I won't quit my day job. The chickens crossing the road here was actually fascinating. On the video, there's a straggler at the end. The Tesla vehicle sees this and knows the right thing to do is just wait for the slow chicken to get across the fucking road before driving. We then saw the additional video with the geese, ducks, whatever, they're not chickens. You see the Tesla vehicle making a decision. It stops, right? Can't drive over these little fuckers. They're not moving. They're still, okay, I can just reverse a little bit and go around them safely. And just to be clear, Tesla hasn't written code of what to do when you see some chickens, ducks, geese, or any other animals on the road, standing still, crossing, right? It's just learned what to do in these type of situations for an enormous amount of training data. Which brings us to the next point. Data. Tesla's the only company on Earth with a fleet of millions of vehicles collecting data that has been collecting data for many, many years. And importantly, as we saw the demonstration with the pickup trucks spinning out, the side-by-side comparison with when the Tesla vehicle began braking, with enough examples of these types of edge cases. The Tesla vehicle has learned without being told explicitly, oh, if a truck looks like it's spinning out or brakes are slamming on, you better stop because shit's about to hit the fan. Instead, Tesla vehicle realizes, okay, that ain't good. Bro is braking violently. Something's probably wrong here. I better start braking too. Bro's sliding across. Uh-oh, shit's hitting the fan here. Better stop. I think the subtitle here really sums it up. Large data, e.g. Tesla's gigantic fleet of millions of vehicles, gives extreme generalization and proactive safety. Now, even a midwit human, if they're paying attention, sees this scene playing out and starts braking themselves, right? But if you haven't developed a general solution to driving, you've never encountered a situation like this before, let's say hypothetically you're a brain dead Waymo, just hypothetically, you're probably going to be a lot later to start hitting the brakes. Because at the point where this vehicle is spinning out and braking violently and moving across, unless you have the predictive power to go, hang on, braking violently, that's not normal. Spinning out of control, that's not normal. Going to collide with that, that's not normal. Going to collide and then, better stop. If you don't have a general form of intelligence and a general ability to drive, you don't have enough information. You can't proactively brake because you can't generalize this scenario because you haven't encountered this exact situation before. This is an underappreciated aspect of Tesla's enormous fleet of vehicles and the, as we heard, Niagara Falls of data. This was also a rather fascinating demonstration. I don't want to get too far in the weeds again, but what's happening here, in short, in the middle here, a Tesla vehicle is reconstructing its best guess of what the 3D scene it's currently driving through looks like based on inputs from its cameras, which are 2D inputs. This is what a human does subconsciously when we're driving. You don't need to see, for example, the other side of a vehicle to know roughly what its shape is and roughly what it's going to look like on the part you're not currently observing, on the other side. We can see a traditional approach to this. Objects that are fairly close look pretty decent, but the further away you go, the more manky and weird things look. This is extremely impressive, and remember, this is being done, this 3D environment being constructed without a single LiDAR or sonar or gaydar involved. Yet still, somehow miraculously, an incredible, very consistent 3D environment is generated as the vehicle drives through it. And again, we're seeing details, not just what the cameras can actually see, but what they don't see being constructed, just like a human does in their brain subconsciously when driving. And you can see the comparison, the traditional model versus how Tesla's pulling this off, night and day. I just want to scrub back and forth and just pay attention to the middle here, right? This is all being done, and we can see on the bottom here, this scene being generated from the camera inputs, which are along the top here. The same stuff. A 3D environment constructed, vision only. I repeat, there is no LiDAR involved here, yet somehow miraculously, just like a human does, the vehicle is creating a 3D construction of the environment in which it is driving and doing a very good job. We saw in this demo, able to spin the camera around, look throughout the environment. This is very impressive. Another rather impressive thing, which I don't want to get too far in the weeds here, but Tesla actually able to essentially talk to FSD and say, hey, bruh, why'd you do this? And FSD says, well, actually, here's why I did what I did. If you guys want to pause and nerd it out a little bit, I recommend it. It's actually quite interesting to read through this detail. But it's very cool that Tesla's engineers can effectively question the software and get a language-based explanation of why it does what it does. And now, some of you may not have quite picked up what we were seeing here, but on screen now is not a feed of Tesla's 8 cameras. This is a simulated scenario. This is not the real world. This data, this stream is being generated. 8 independent camera feeds, as if a Tesla vehicle were driving in the real world. This is entirely fiction. It's not real. Would anyone watching this have been able to tell had it not been pointed out? Surely not. It's worth noting that the simulation here isn't just of the different angles, but includes camera distortion, the actual color palette, the resolution of the cameras as well. It's like for like, near perfectly simulated data. Extremely impressive. Something else really fascinating we learned about was the ability for Tesla to re-evaluate their current build of FSD, let's just dumb it down a bit, with historical data that they've captured from the fleet to see how the new software, the current build or a potential future build, would handle the same situation. The example here, the original, the Tesla vehicle, probably a little bit close for comfort for the pedestrians here, walking at night around a vehicle. So Tesla can, in essence, run through their archive of historical data and footage of situations, edge cases, and so on, and see how's the new build react to this situation. We saw the example, it gave a much wider berth. There were also the synthetic adversarial options as well, where Tesla can simulate some crazy shit happening. So they've got some original historical footage from an actual event, but they can change a few things. For example, this vehicle just flying across a few lanes out of nowhere. This is a great opportunity for Tesla to test their software in situations that may not arise that often in the real world, but they still want to make sure, understand how the vehicle would perform. The closing remarks, answering the question, what's next? The answer to that, of course, would be to unlock Tesla's entire existing fleet, to enable their entire existing fleet of vehicles, 8 million-ish and counting, to be fully autonomous. Then mass production of Cybercab. Oh, and P.S. one more thing, also all the stuff we've done with FSD/autonomy transfers to the Optimus humanoid robot, which is going to be gigantic. And the final point was the whole point, which was the AI recruiting effort. Dear Gigabrains, you like what you see? You want to help work on Tesla's AI projects, multi-trillion-dollar opportunities, having a huge impact in the real world? Come work at Tesla, bitches. Tesla.com/AI, which, by the way, is now up on screen. Notice, Tesla.com/ I don't know, for example, Model 3 takes you to the Model 3 page. You can buy one. AI isn't just Tesla jerking themselves off going, hey, look how cool we are. It's on the careers subsection of the Tesla website. This clearly shows Tesla's priority is to get shit done, and they are aggressively recruiting the best AI talent in the world. This page, again, is not for investors. That presentation was not for investors. It's to recruit AI talent. Optimus, see opportunities, and of course, there are a bunch of Optimus-related jobs. If I continue to scroll down the page, build the future of artificial intelligence. You can submit your info and your resume to Tesla to apply for an AI-related job. I'm just going to read this paragraph, and then we'll wrap. Quote, we develop and deploy autonomy at scale in vehicles, robots, and more. We believe that an approach based on advanced AI for vision and planning, supported by efficient use of inference hardware, is the only way to achieve a general solution for full self-driving, bipedal robots, e.g. 2 legs, Optimus, and beyond. I would just like to close by saying we still don't understand why I've been buying Tesla stock hand over fist with every spare cent and haven't stopped. That's very unfortunate for you. See you in a decade. Want more content? Early access? Bunch of perks? Click the links in the pinned comment. AG1 has been part of my daily health protocol for almost half a decade. It's packed full of vitamins and minerals and helps me fill in nutritional gaps while supporting energy, digestion, and immune function. It also has prebiotics and probiotics to promote gut health. I take my health very seriously, and so should you. Try AG1 today by visiting drinkag1.com/SMR or click the link in the pinned comment and enjoy a free welcome kit with vitamin D3 plus K2 and AG1 travel packs. That's drinkag1.com/SMR.